what we had at the end of class last time was that a function, so we had an open set, say, in Rn mapping to Rm. We said f is continuous at A if and only if what? So for every sequence xk converging to A, we have f of the sequence converging to f of A. And so the forward direction, proving if it's continuous then this is true, was just an application of understanding what it means to have convergence, that if xk's are converging to A, then by continuity, we know that points near A get mapped to points near f of A, and so the f of those xk's ultimately end up having to get closer and closer to f of A. The converse, knowing if it's true for every sequence, that therefore the function must be continuous, that was the hard part in terms of the logic structure. But what I want to do today is use this to do a bunch of things. So the first application I want to do is going to be fundamental for all sorts of calculus stuff we start doing soon. Remember the word level set? When we talked about contour maps and isobars and isotherms on the weather map. So what? Speaking of climate, right? So if f, say, maps some open set in Rn to Rm, recall that a level set so we called this a level curve when n was 2. So we had the map of the United States, which is a two-dimensional object, the map is. And then we looked at where the temperature was constant. We called those level curves. And if we were in 3 space, we called them level what? Surfaces. But in general, you can talk about a level set. And it doesn't have to be a real valued function. You can have a vector over here. You can have several functions. You could be looking at points where pressure and temperature are both constant. Might not be a very interesting thing to look at. But
was it word level set from scalar value functions?
Right, we were doing it for scalar value, but I'm saying you could have several scalar value functions. For example, you could be off in 3 space, not just on the map of the United States, but you could be looking at all of space and look at points where temperature is 10 degrees Celsius and pressure is, I don't know. What's a good?
1 atmosphere.
So fix a reasonable value for pressure.
700 bars? Yeah, just an atmosphere.
Yeah,
It's a bit less than atmosphere, I think. Oh, yeah.
Okay, fix one of those. Fix a temperature. Then you're fixing a point here in R2. And we look at f of a point x is the temperature at x and the barometric pressure at x. If you now want to talk about a level set, you're setting this equal to a constant vector. That's where both functions would have a constant value. So a level set is the set of points x in the domain with f of x equal to some constant vector, fixed vector in Rm. And then what's interesting to do is vary the constant and look at the different sets. So what would you expect in this situation where you're looking at temperature and pressure in 3 dimensions? What would you expect the level sets to look like? Okay.
I don't know if it's exactly what you're asking, but just like basic physics, that if the temperature one is going up, the pressure would go up and vice versa.
Oh, okay. You're actually saying that for an ideal gas, these are related.
Yeah, I think that's what you were asking.
Like
But I'm thinking of just...
But isn't it only a fixed volume though? This is like the atmosphere.
Right, so I'm actually thinking about
How would you
go off into space.
Looks like some three-dimensional
like
like
how would that work? That sounds
thing. It
crazy.
could either be.
Okay, you guys are micromanaging here. I'm not trying to do a whole course on the atmosphere. I'm just trying to be heuristic here. If you fix a temperature, intuitively, what dimensional set would you expect to get? We're in 3 space now.
2.
You expect that one constraint should cut down your degrees of freedom by one thing, and so you should have surfaces where temperature is constant.
And then pressure.
And same for pressure. So if you fix a temperature, you expect to see something like this. Temperature equals some constant. And if you fix a barometric pressure, you would likewise expect to see some sort of surface. And you might expect that generically those 2 surfaces should intersect along
Some curve.
a curve. So this would be the level set of the function f. This would be the set of points where f of x is C1, C2. Does that make sense?
Just to clarify, since that graph lives in R5,
I'm not doing a graph, right?
but fixing one of those constraints would bring it down to R4, I guess?
No, I'm not doing graphs.
Okay.
So remember that level sets always live in the domain. So I'm graphing the level set of T, I'm graphing the level set of P, and I'm saying to have this joint function be equal to C1, C2 is where the 2 surfaces overlap.
What if the 2 surfaces are the same?
Then you get a whole surface.
Okay.
That could happen. That could happen. But in general, a level set is just going to be the set of points where you have a certain constant value. And we're going to spend a little bit of time this semester, but a lot of time spring semester studying such animals. Now, here's the question I wanted to raise. So here's a notation for this. The set of points x in U such that f of x equals c is often denoted, and this is going to start a controversy, but I'm going to say it, f to the -1, read f inverse, of the point C. Do you guys want to complain?
Probably yeah. Sure.
What are you complaining?
There are multiple x values.
So what notation have you seen this in? In what context have you seen this notation before? Even in this class? Inverse function. You're going to complain to me
That's what I was thinking.
that this function doesn't have an inverse. Right? Because here's a whole curve where the function equals C1, C2. So what would f inverse of this mean? There's no unique x to go back to. So this notation does not mean inverse function. So the warning here, f inverse does not denote an inverse function. here's what you should be thinking about when I write this. I'm going to draw you this sort of picture of a function as a mapping from a set to a set. F takes points here to points here, right? If this is an x, this is f of x. Let's forget vector signs, let's just use letters. F of x. The F inverse asks, take a set here, call it Z. F inverse of Z denotes all the x's back here that land in Z. So it's just saying, what are all the x's back here that map somewhere in this set Z? And that's this. And it's often read the preimage of Z under F. So do you understand the language? If a function's mapping this way, you can think of f of x as the image of x.
Okay.
The value of f taken at the point x, you can think of as being the image of that point. And the pre-image is saying, what are all the x's that landed wherever?
And so you can take a pre-image of an entire set of values?
Yes. So in this case, I'm taking the pre-image of the unique point C, but I could take the pre-image of an entire set and ask, what can you say about it? So it's just a fancy way, and if f were eligible to have an inverse function, this would be doing the inverse function. But it's more general. Allison, does this make sense at all? So I'm basically thinking of a function as this sort of thing that sends stuff here over here, and I'm asking who back here lands in Z somewhere. Here I'm asking who lands at the value C.
Just for clarification, the x's in your definitions of z or y, are they also vectors?
Well, I was doing this just in a setting of sets without, in our applications, everybody's vectors, but I'm just trying to say this is the language of just general sets. So here's the question I have for you. Suppose you had F mapping R2 to R. And suppose, let's use a word we've now learned, it's continuous. Could a level curve of F look like this? So it's a function on the plane. So you're thinking, for example, of temperature varying, and assuming temperature is a continuous function. Could the set of points where the temperature is 100 degrees look something like this? So do you understand what I put little open interval marks here, and I put a gap here. Could that be the set of points where the temperature is 100 degrees? Conceivably, for some really weird hot day.
No.
I'm seeing lots of no's. And a few mouths too, but lots of no's. So people that are saying no, why?
Because the limit as x approaches
the whole is not f of the whole.
You're exactly on the right track.
Isn't it, because like in calculus, the theory that like, I don't remember exactly what it's called, but like your slope, like you can't like all of a sudden like have like the overall slope that's not involved in it. And like temperature, because temperature's like the change in heat, because it's like a slope, then it has to like.
So, yeah, of course, you're talking about more structure than I have thinking about slopes, because I'm only talking about continuity. But continuity is exactly along the lines of what Sammy's saying.
Perhaps it's just like you can't have x approach a at that point because a is somewhere else, so.
Well, no, so I think what you guys are suggesting is that I should call this point here A. And Sammy, you were thinking of approaching A along this yellow curve.
But if x approaches, x wouldn't approach a, would it? Or
No, f of x would.
No, f of x would approach
Yeah.
A.
Right. So suppose that on this yellow curve that I drew here, that this was the level curve where f of x was equal to 100. All on the yellow curve. And I believe Sammy's suggestion was, consider a sequence of points converging to A, where xk's are all in the level curve, and A is not. Right? We were stipulating that there was a gap in the level curve. So f of A is something other than 100. So f of the xk's are all 100, and f of A is definitely not 100. Do you see that we have a problem?
So you have.
So what did we say is supposed to be true if you have a continuous function?
Approaches f of A.
F of xk's are supposed to approach f of A if f is continuous at A. And I told you f was continuous everywhere.
So that dot up above, like where the hole is, that dot doesn't denote that it's 100 at that point?
It does.
It does. So it doesn't.
But these are different points, right?
That's not it.
So this happens to be a spot around and it's cooler, say, but at that one point for some reason it's actually 100.
Got it.
Not too plausible, probably.
Right, no, because
But I'm more worried about what's going on down here. I just put that there to confuse you.
you're not gonna have some instantaneous point where you walk through and it's gonna be a different temperature.
You could.
You would have to.
I mean, in real life,
The temperature around it would have to be
You
different.
can't have
You couldn't have like an instantaneous point next to each other, it'd be two different
sure
temperatures.
you
You
could.
can't have a temperature at an instantaneous.
Well, I don't know what instantaneous point means anyway.
Well,
But I mean, think about it. We're modeling temperature so that here it's varying as you walk this way.
Right.
When you're walking this way, it's 100 only there, and here was 98, and there was 102. I don't know.
but it has to be, all of the other temperatures have to exist between two different points of temperature.
So you're
Unless you have
saying,
some sort of
you don't believe that I can have an isolated point where it's 100. You
Right.
think there should be a curve of points.
Well, no, you could have one isolated point, but all of the points around it would approach up to 100.
Right, but
And
that
depth.
would still make the level curve look like this. The level set would still look like this. If around this point, say we're a local maximum for the temperature,
Right.
which we'll talk about a lot in a few chapters, then it would be, near this point it would be a peak on your mountain, on your temperature mountain. It would be the highest value, and nearby your level sets for lower temperatures would look like curves going around like that. So this picture could happen. Let me move on. We got a problem here. Right? By our proposition from yesterday, if f is continuous at A, and if you take any sequence of points converging to A, then f of xk's must converge to f of A. what are the f of xk's equal to? 100. You have a sequence 100, 100, 100, 100, 100, 100, 100, 100, 100, dot, 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 dot. What does it converge to?
100.
100. So you can't have f of a different from 100 if the function is continuous at a. Yes, Matthias?
The problem isn't necessarily with the fact that like where A is, like the actual dot is far away, but that there's a gap in A, right? Because if you
No, A is just this point in the plane, in the domain.
Right.
This dot that I drew really was to confuse matters, and I see I succeeded.
Yeah.
So it just that doesn't matter at all. The
It's
real
totally
problem is
irrelevant.
the gap.
All I'm caring about here was the gap right near A, right?
Okay.
So what's after eight?
What about the
But we're not, we're just.
Yeah, what about the other?
Hmm?
What about the other part?
Yeah, and similarly, what about over here?
Is that a gap? Okay.
I put open interval signs on there.
Oh, okay.
Can that happen? No,
No.
by the same logic. If you take any sequence of points converging to here, the value at the limit of that sequence must be the limit of the values. They're all 100, so the value at the limit must be 100. So in fact, you've got to close it up and have it be 100 here too, and 100 here too as well. What did we just prove about level sets of a continuous function? What kind of sets are they? Closed. That's what we just proved. And that's going to be super important as we go on later on in the semester. So we have thus proved that the level sets of any continuous function are closed sets.
Or you can put accent on the E then.
Any sequence of points you take in the level set that converges to a point, that point likewise has to be in the level set. Because the limit of a constant value is that same constant, right? A sequence of hundreds can converge only to the point 100. Guys get it? Now, I'm going to claim we proved a bit more. Indeed, we really have proved more. If Z is any closed set in the range of your function, not just a point, but any closed set, what can you tell me about the preimage? Namely all the x's that map to Z. F is continuous. Still, F is continuous. Then the preimage of a closed set is always closed.
So because the preimage is a contour.
Well, I'm generalizing the level set notion where you just take the pre-image of a point, right? So the level set is the situation where Z is just a single point. So if I asked you, consider all the points where the temperature is between 95 and 101 inclusive. Take the closed interval and ask yourself, at what points is the temperature any number between 95 and 101? That's going to be a closed set of points. So you could imagine looking on the on your map And you could imagine trying to sketch in level curves. Here's where it's 101. Here's where it's 95. I'm just imagining, I'm not saying this is necessarily true, but then all the curves for the temperatures in between fill in. Now you might have some gaps, but you can imagine filling in with different temperatures as you vary between 95 and 100. But you're going to fill in and have an entire closed set filled in here. You can't have little gaps in the set any more than you could have gaps here in the curve. So when you fill it all in, it's actually going to be everything between the yellow and the red, for example, with no holes in the region. There could be holes, but you'd still have to have the boundary of the hole in there. Okay. So what's the proof of this? We proved this one. How do I prove this? Tim, is there a question?
Yeah, what does let's say in the brackets for z equals
The set C. Because I was looking at the set of points with the function equals C. It's the set consisting of vector C. Sorry.
Okay, cool.
Sorry. So how do I prove something is a closed set? So let's prove this one. So I have to take a convergent sequence of points in the set. Suppose I have a sequence of points xk converging to somebody, and the xk's are all in F inverse of capital Z. That's the set I'm trying to prove is closed. We want to show what? What do I want to show about A? That A is in this as well. Okay. Tell me what to do. Hint. Tell me what this means. Matthias?
F of xk equals, or is in Z.
Right. So let's give it a name. You wanted it to have a name. Let's call it y sub k. This is f of x sub k. And by definition of this symbol, which is written right here, yk belongs to Z. Finish the proof for me.
So
Remember, f is continuous. You got to use it somewhere.
as xk approaches A, then f of xk approaches f of A.
Good. Since f is continuous at A, limit as k goes to infinity of f of xk is f of A. Okay?
And
Now these are the yks, and they're converging to the point f of A. Someone want to finish it?
are we, sorry, oh, we're proving that f inverse is closed, right?
So what we're trying to show here is that the point A is likewise belonging to this preimage of Z. Now what you've told me, Matthias, is that f of A is the limit of the yks.
If f of A is in Z,
Well, we're trying to show it is.
Since
Because that's usually close.
f inverse is a closed set, yeah.
So what do we know about Z? It's closed. What do we know about the
That's what we're
YKs?
talking about. Okay, yeah.
It's that they use
It's in the numbers.
These are in Z. So this is a sequence of points in Z converging to this point.
So that point must also be in Z.
Because Z is closed, the limit of the sequence must be in Z. So the YKs are in Z. The YKs converge to F of A. And Z is closed. So by definition of a closed set, if you have a convergent sequence of points in the set, the limit must likewise be in the set. Therefore, F of A is in Z, which means I get to be fancy and say whence. First time in the whole class I've been fancy. Whence what? A
is in the preimage.
A is in the preimage, and that's what we wanted. End of proof. Any questions on that? So, as our video experts can testify, this particular fact will get used literally dozens and dozens of times as we proceed. You're going to want, for example, to know that you can solve a max-min problem for a continuous function. And the fact that there is a solution is going to follow because of things like this. All right, I want to do another consequence for you. Composition. Suppose, I'm going to draw you a diagram here. Suppose you have two functions. What do you think I'm going to do? Composition. So suppose you have something like G mapping an open set in RL to some open set here in Rn, and F is mapping to Rm. And suppose I have a point here A, and G maps it to a point D in this set. So I'm going to write this all down officially. So suppose G maps U in RL into Rn, sorry. F maps this open set in Rn to Rm. And suppose G is continuous at A. And where do you think I'm going to want F to be continuous?
G of A.
G of A. What do you think we want to conclude? Fog is continuous at A. So the composition of continuous functions will be continuous, but I'm being a little bit more precise here and doing it only point by point. That's important, right? And we're going to want to know in approximately a week that you can say the same thing about differentiable functions, and that there's some rule that has something of a name related to something you learned in high school that allows us to take derivatives of compositions. So compositions of functions, you will all agree, are important things because most functions are built by composing other functions. So you can see that this is going to be an important ingredient. How do I prove a function's continuous?
Show that as
I'm going to use, I've erased it now, but I'm going to use what I was recalling from yesterday here. We have this characterization of continuity in terms of sequences. So if you want to prove fog is continuous at this point A back here, what should I do? Take a sequence. And remember we talked about this yesterday, where we need to know that it's true for arbitrary sequences, for every sequence, right? Because, proof. Suppose x of k is an arbitrary, i.e. any sequence in U converging to A. Well, let's look at what fog does to that sequence. How do I compute fog of somebody?
F of G of X.
What happens as k goes to infinity? Xk goes to A, but where does g of xk go? Because?
G is continuous at.
Because g is continuous. So because g is continuous at A, g of xk converges to g of A. And g of A was otherwise called B. Now what should I write for my next line?
F of G of A equals F of B.
Because f is continuous at B, f of this sequence converges to
G of A, which is equal
F
to B.
of B.
It's annoying writing all these vector signs. I don't blame you, you leave them off. But I won't. Well, let's see. So I took any old sequence xk converging to A. And what did I just show happened when I fogged it?
It equaled the F of the composition.
It equaled fog
Of A.
of A. What does this tell me?
But it's
Fog is continuous at A. So the hard part of the theorem we proved yesterday was, if you know it works for every sequence, then the function's continuous. So I'm using that theorem both ways. I'm using it one way here, and then I'm using the hard converse by the hard converse. It follows, because for any sequence, xk converging to A, we know that fog of xk converges to fog of A. Fog is continuous at A. So if you knew this was true at all, if you knew that G and F were continuous on their domains, and the domains fit together properly, yeah, you have combinations continuous. Okay, so this is officially proved, and I want to just point out that you can now go back and put a nail in the coffin of some of those limit problems we were discussing. which one of these I did. Is this what I did? Is that how I had the x's and the y's? So start with this function when you're not at the origin, and 0 at the origin. What did we decide about this function? Is it continuous at the origin? Remember what,
we decided.
when you see a pattern with the exponents like this, you should remember that we discussed this weird example.
X equals y squared.
So, is f continuous at the origin? It's the question, you know the answer, but I'm going to apply what we just proved. Consider the curve g of t, which is t squared t. So I'm doing a situation here where I'm mapping real numbers by g to R2, and then I'm doing f. What is my curve g of t looking like? It's the sideways parabola, which we were looking at the other day. In fact, what would be true if f were continuous at 0? What would we know from this picture? No. If f were continuous at 0, is g continuous?
Yeah.
Right? Its component functions are certainly continuous, and pretty much by the kinds of things you did in homework, if you have a function whose components are continuous, then it's going to be continuous. So if f were continuous at 0, since g is continuous at 0 and g of 0 is the origin, we would conclude, from what we just proved, that what about fog? The fog is continuous at 0. Right? That's what we just did here. 0 goes to the origin. If f were continuous there, then fog would be continuous. All right, well, tell me what fog is. What's fog of t? So just plugging all this stuff in here, right? So I have t squared over t fourth plus t to the fourth. That's a half whenever t is in 0. And what's fog of 0?
0.
Well, when I put in t equals 0, I get 0, 0. I go back to this rule and I say it's 0. Is this function continuous at 0?
No.
No way. What do you conclude? What's wrong? Yeah, I gave it away, right? I threw in the subjunctive when you were not expecting it. Some of you don't even know what that means.
So can we use that kind of method on
Absolutely.
these funky limit problems?
If you want, absolutely. If you can find, what is, so let me just write the conclusion. Conclusion, f is not continuous. So this is basically just formalizing what I was doing the other day when I said if you're coming in on different paths and you get different limits, you don't have a limit.
So we just knew to pick t squared t based on the other day.
Right. In fact, there's going to be a challenge problem coming up that asks you to generalize functions like this and put in random exponents and ask when, in terms of the exponents, when is it going to be continuous and when isn't it? So those of you who find this sort of interesting to figure out where did the guess of looking at of x equals y squared come from other than looking at the picture on Mathematica, I encourage you to actually investigate that as these challenge problems unfold. Okay, one last comment, and then tomorrow we're on to chapter 3 in derivatives. And there was much mirth.
And there was much rejoicing.
Yay. One last comment. You will notice if you actually read the book, ha ha ha, that I've done this stuff a little differently from what's in the book. Remark, the book discusses preimages not of closed sets, but of open sets. And there's a theorem proved in the book that says f is continuous if and only if the preimage of every open set is open. But you guys are getting good at this game. How would we relate this result to what we've just done today?
The complement of any.
You do complements. And it just becomes a chase of sets that the preimage of the complement is the complement of the preimage. So the exercise that you need to, if you wanted to finish this, would be if you have f mapping Rn to Rm, and you had a set Z here, any open set, its complement is closed. So if you had an arbitrary open set, you could take its complement, and that would be a Z. And you can take the preimage of the complement of Z, and what you would want to check is that's the preimage, the complement of the preimage. So that's the exercise. And if you write down definitions, it's actually very easy.
Why is it not Rn minus?
Yes, M.
Oh, I have it backwards.
Z and Rn.
M there and N here. Thank you. So if we've proved preimage of a closed set is closed, and Z is any closed set, I will then show the preimage of its complement, namely an arbitrary open set, is the complement of a closed set, namely it's open. But you can also read the proof that's done directly in the book, which is rather different. It works with actually finding little balls around points and making sure you're using the definition. It's actually the case, I believe, that the way I've done it is less painful for you, so I have only you in mind when I do it this way. Okay, so we're done with chapter 2. On to chapter 3 tomorrow.